our syllabus in this course, but let me talk about vector spaces because we need these notations and content. At the first, we see the definition of complex number, okay? And you know this definition, but I review this rapidly. A complex number is an ordered pair such as A and B, where A and B are real numbers, but we write this by this notation so that these two are equal, okay? These two are equal. The set of all complex numbers is denoted by C, so that C equal to this element for each A and B in real numbers, or the set of all ordered pairs such that A and B belong to R. Addition and multiplication on C are defined by these two. This is addition, A plus BI plus C plus DI equal to A plus C. These real numbers must be added together, and these two added with together. And this is the definition of multiplication in complex number. A plus BI multiplied by C plus DI equal to this complex number for any two complex number. Please note that A, B, C, D are real numbers. And for any A in R, we identify I plus 0I with A. Thus we think of R as a subset of C. Any element of R can be considered as this form as a complex number, okay? We also usually write 0 plus BI as BI and omitted this 0, and we usually write 0 plus 1I as I. You should verify that I to the power of 2 equal to minus 1, and this is very obvious because by our definition of multiplication, okay? By the definition of multiplication. Multiply C, for example, plus DI, C plus DI to AC minus BD plus AD plus BC, okay, plus I. So that if we consider I2 equal to I multiplied by I, and this is equal to 0 plus 1 this is equal to 0 minus 1 plus 0 I. and this is equal to minus 1. Okay. And any real number can be considered as a complex number. If these are all order pair, okay, all order pair, A and B, A and B, okay, or with this notation A plus IB, then any element in this axis have this form, x plus 0I, or this is equal to x and 0. We identify x and 0 with x, okay, with x, or this equal to x, so that any real numbers is a complex number, and we have this inclusion. These are real numbers as a subset of or plan or complex number. Okay, this is a review for complex number, and the definition of real part and image part of complex number. Suppose z equal to a plus bi, where a and b are real numbers, so that z is a complex number. Okay, the real part of z denoted by real of z is defined by a, first coordinate, and the imaginary part of z denoted by image of z is defined by image of z equal to b, the second coordinate. Okay, the absolute value of z denoted by this and defined by this equality, so that absolute value of any, if we consider this as or z, this is the distance of z to origin, so that this is absolute value of z. Okay, and for any sequence in complex number and any element of complex number, this limit means the limit of this distance equal to 0. This is the definition of limit in any metric space. Okay, and we have this easy observation that the limit of sequence equal to n if and only if limit of real of z equal to real of this limit, and the limit of image of this sequence equal to the image of this limit. Okay, this is very easy. Now we can define measurable complex value function. Suppose x and s is a measurable space, a function f from x to c. Please note that in the previous session we always consider function from x to real numbers. Okay, dear students, do you have my voice? Don't have any problem? In the previous sessions we consider function f from x to r real numbers, but this function has value in complex number. F is from x to c. This function is called S measurable if real of f and image of f are both S measurable function. Please note that real of f and image of f are function from x to r. Okay, for any function such as f from x to c, real of f is a function from x to r, and image of f is a function from x to r, and f equal to real of f plus I image of f. Okay, because any element is in complex number, so that we have f of x equal to real of f of x plus image of f of x I. Okay, and we found this real and image part. This image and image are real functions, and we know the definition of measurable real valued functions. We use this definition if these two real valued functions are S measurable. We say that f is S measurable function. Okay, so that this is the definition, that f from x to c is S measurable if and only if real of f from x to r and image of f from x to r is S measurable. Okay, and these two are equivalent. Okay, this is the definition of measurability in for complex numbers. Measurability for complex numbers, complex valued functions, complex valued function. Okay, okay. Okay. And we have this proposition: suppose x and s is a measurable space, f from x to c is an S measurable function, and p belong to this interval 0 infinity, then absolute value of f to the power of p is an S measurable function too, so that this power of f is measurable if f is measurable. Okay, and this proof is easy because the functions real of f to the power of 2 and image of f to the power of 2 are S measurable because the S square of an S measurable function is measurable, but by example 2.45. Please note that if we have a measurable function, okay, if we have a measurable function that combined with a continuous function, this is continuous and this is measurable, for example. This combination is measurable 2, okay, so that we see that if f from x to c is S measurable, we have real of f and image of f are S measurable, okay. So if we combine these functions with the function with this function rules, we see that these two are S measurables too. Real of f to the power of 2 and image of f to the power of 2 are S measurable, okay, are S measurable. And so that its summation is S measurable because the sum of two S measurable function is S measurable by 2.46. Now this function is S measurable because it is a composition of a continuous function on this interval and an S measurable. This theorem that I mentioned for you, composition of any continuous function, and if G is a continuous function and if be a S measurable function. Then GOF is S measurable too, okay. Now we know that real of f to the power of 2 plus image of f to the power of 2 is S measurable. Consider this as in this f, for example, okay. If you consider this as f1, for example, f1 is S measurable and G1 equal to this function g1 of x equal to x to the power of for example p divided by 2 is continuous. Okay, so that g1 of f1 is measurable. But g1 of f1 of x equal to g1 of f1 of x, and this is equal to real of x to the power of 2 to the power of 2 plus image of f of x to the power of 2, all of this by this power. Okay, so that this function is measurable. This function is measurable. In other words, this is an measurable function because this equal to, we can continue, this is equal to real of f of x to the power of 2 plus image of f of x to the power of 2 by this power, then by this power. Okay, and this equal to absolute value of f to the power of p. Okay, because it's very trivial, because we know that absolute value of any element such as this equal to this a2 b2 to the power of this. Okay, okay, so that if f is measurable, the absolute value of f to the power of p is measurable too. Now we have this definition. This is very important for you. In integral of a complex valued function. Integral of a complex valued function. I emphasize again that in the previous session we define integral and integrability for functions such as f from x to r or x to, for example, this extended real valued function. Okay, no rf or function is from x to c complex number. Okay, f is a function from x to complex number. Suppose x is and mu is a measure space and f from x to c is an s-measurable function with this property, f is integrable with respect to mu. The collection of such function is denoted by L1 of mu. Then the integral of f is defined by this. This is the Lebesgue integral of f with respect to this measure, with respect to mu. This integral equal to integral of real part plus I integral of image part, imaginary part. Okay, so that we have two notation and they are very important. Let x is mu be a measure space. Okay, L1 of mu equal to the set of all f from x to c such that f is s-measurable and the integral value of f d mu be finite. Okay, on x. This is L1 of mu. Now, if f belongs to L1 of mu, we define the integral of f d mu on x equal to the integral of real part of f d mu plus I multiplied by integral of image part of f d mu. We can write or omitted this x. In the book this x is were omitted. Okay, or set and or contents of this integral all is x. Okay, and this is the definition of complex valued function on x. Complex valued function on x. The Lebesgue integral with respect to mu equal to this summation. Integral of real part plus I integral of image part. Okay. The integral of a complex valued measurable function is definable only when the absolute value of the function has a finite integral. In contrast, the integral of every non-negative measurable function is defined, also the value may be infinity. And if f is real value, then this integral is defined to be integral of f plus minus integral of f minus if at least one of these two are finite. This is a review of previous definition. Please remember that for a function f from x to 0, infinity, or even this interval, this integral is defined for any function, for any s measurable function, and this is a have a value in this interval. Okay. In the second step, if is a function from x to this, and that real value function. Okay. And that this integral is finite, or this integral is finite on x, we define the integral of f d mu equal to the integral of f plus d mu minus integral of f minus. We see this definition, so that this is the definition of real valued functions or extended real valued function, and this is the definition of complex valued function. All of them must be s measurable. Okay, all of this function must be s measurable, this function and this function, and also this function, because L1 of mu is the set of all s measurable function with this property. Okay, you can easily show that if f and g from x to c are s measurable such that all of these are finite, then we have this equality, and also it is equality for all alpha. This is very, very easy, because for any f and g from x to c, it is very easy that real of this function equal to real of f plus real of g, and the image of f plus g equal to image of f plus g. Okay, so that we have integral of f plus g d mu plus I integral of image of f plus g d mu g d mu. Okay, is equal to this plus I integral of image f d mu plus integral of image of g d mu. And now we can write these two inside and these two, so that this is integral of real d mu plus I image d mu plus this and this, the integral of real of g d mu plus I image of g d mu, and this is equal to integral of f d mu plus integral of g d mu. Okay, this is integral of f and this is integral of g, and the proof of this very easy, and you can write it for itself. And we have this proposition, a bound for absolute value of an integral. Suppose dear students don't have any problem, you see my image and you hear my song. Dear students don't have any problem. Mr. Ghassan, Mr. Muhammad. Suppose x s mu is a measure space and f from x to c is an s measurable function such that this integral is finite. Then we have this inequality. The absolute value of integral is less than or equal integral of absolute value, so that we have a bound for absolute value of integral. Absolute value of integral. This is the bound for this, okay? And its proof is easy because the result clearly holds if this integral equal to 0, okay? If this integral equal to 0, then it is clear that this integral is we have this integral equal to this integral, because for any, if we put alpha, these two are omitted, okay? It's very trivial. And we can move alpha to the integral, and integral of this function equal to integral of real part plus image part for this function, okay? By the definition of complex value integral, complex value integral, integral of real plus integral of image. Our function in this theorem is alpha f. Okay, integral of alpha f equal to this. But this equal to this because we know that this is a real number. This is a real number. So that this imaginary part must be 0. Because the summation is a real number. So that this must be equal to 0. This equal to this. And this is less than. Note that these two are real valued functions. Real valued functions. And this is equal to. Please note that for any two functions, for any if for example f1 and f2 are two functions from x to r such that f1 is less than or equal f2 almost everywhere, then the integral of f1 is less than or equal integral of f2. Okay, we have this proposition. Now we have these two real values. This, for example, is f1 and this is f2. We know that real of this is less than or equal absolute value. This is very trivial that for any function real of f and image of f is less than or equal absolute value, because this is equal to this real to the power of 2 plus image to the power of 2. Okay, so this 2 is less than this. This is less than this function, so that its integral have this order 2, and this is equal to absolute value, because absolute value of alpha equal to 1. Absolute value of this equal to 1. So that absolute value if absolute value of alpha equal to 1, then and we have the definition of complex conjugate, that bar. You know this definition. The conjugate of z denoted by the z bar equal to real of z minus image of z I. So if we have, for example, z equal to x plus iy, then z bar equal to x minus iy. Okay, x minus, this x is the real of z and this y is real of z, and this is image of z. Okay, so that this is equal to real of z minus image of z I. Okay, we have this definition. For example, if z equal to 5 plus 7i, z bar equal to 5 minus 7i, and other examples. We have these properties of complex conjugate for any w and z in complex number. We have these equalities. It's very easy because you can use the definition of multiplication. If z equal to x plus I, then we see that z bar equal to, or z bar equal to x plus iy multiplied by z minus iy. Okay, now use the definition of multiplication in complex numbers. This is equal to x to the power of 2, x to the power of 2 minus y to the power of 2, sorry, plus, because this is minus. Okay, plus two x y x y x y minus x y multiplied by I, so that this is equal to x2 plus y2, and this is equal to absolute value of z to the power of 2, because absolute value of z equal to this radical. Okay, x2 plus y2, this equal to absolute value to the power of 2, and we have this equality, and these two are very easy, and you know this equality, z plus z bar equal to 2 multiplied by real of z, and this equality, these equalities, and these are very easy. Absolute value of z bar equal to absolute value of z, and integral of complex conjugate of a function. This equal to this for every measure mu and every f in L1. All of these are equal, all of these are trivial, and this is easy because the integral of absolute value, please note that, please note that if for example from x to c belong to L1 of mu, we know that this integral equal to this integral real of f minus image of fi. Okay, f bar equal to this, because f equal to real of f plus I image of f, so that f bar equal to real of f minus, and this is equal to integral of real of f d mu minus I integral of image. On the other hand, this is equal to conjugate of this complex number. Please note that this is a complex number. And if we compute its conjugate, this is equal to okay, this is equal to this, because we must multiply in minus 1 to this, and this is equal to conjugate of this integral, because this is this integral, okay, and this is the proof of last statement. Other one is very easy, okay. Now we can define the definition of vector spaces. These definitions are very important, and we write this definition and properties in the next session, but I emphasize that these two sections okay, we see product measures and its properties, but this chapter 6 is very important, and the contents of this chapter is not in your syllabus in this course. For example, metric spaces, open set, closed set, but they are very important. Please read this from the book for yourself, okay? For yourself. But we see this definition in this session: vector spaces, integration of complex valued function, and in the next session we will talk about vector space and non-vector space. Please, I see this definition and okay. Okay. Let me review rapidly this definition, because these are only 2 pages, okay. Okay. In this book and many other books, F stands for either real numbers or complex number, or this is a field of real number or field of complex number, okay. Let V be a set, okay? And addition on a set V is a function that assign an element F plus C to V to each pair of element F and G in V. And a scalar multiplication on a set V is a function that assign an element alpha F to V to each alpha in F and each F in V. So that we have two binary operation, so that one binary operation and another function such as this. For example, plus is a function from V times V to V that maps any ordered pairs to X plus Y. And a scalar multiplication is a function from F times V to V such that maps any alpha X to alpha X, okay? We can write this dot or not, but we have two functions. For any F and G in V, we have F plus C to V. This is this function, okay? For any X and Y, X plus Y must be belong to V. Now we can express the definition of vector space. A vector space over F is a set V along with an addition on V and a scalar multiplication on V such that the following properties holds: commutativity F plus C equal to G plus F for all F and G in V. Associativity, this equality and this equality for all F and G in V and all alpha and beta in F. Additive identity, there exists one zero in V such that we have this equality for all, so that 0 plus F equal to this and equal to F2. Additive inverse, for every F in V there exists one G such that F plus C equal to 0. This is the inverse of G, inverse of F. G is the inverse of F. Multiplicative identity, 1 multiplied by F equal to F for all F in V. 1 is one of our field F, okay? And distributive properties, we have these equalities. Please note that alpha is a scalar number and F and G are in our vector space V. This equality for all alpha and beta in our scalar field and F and G in V. If we have these two multiplication on V, we have this V is a vector space over F. V is a vector space, and you know this definition. For example, Fx for any non-empty set X, if we denoted Fx, the set of all functions from X to F, okay? All functions from X to F. Fx equal to the set of all functions from X to F, okay? This set with these two action, addition and scalar multiplication, is a vector space. In this vector space, Identity for additive is zero function. Function that maps any x to 0, and inverse is this function. If we consider 0 from x to f, by this definition 0 of any x equal to 0, then this is equal to this for any x equal to 0 plus f of x, and this is equal to f of x. And for any f from x to f, we see that minus f from x to f, by this definition minus f of any x equal to minus fx, then f plus minus f equal to 0 function. And other properties is very obvious. A special case of the previous example, if n belong to z plus natural numbers, x equal to 1 to n, then fx is the familiar space Rn or Cn. Okay, please note that. For example, if let me by this function equal to the set of all function from 1 to n to f, and this is equal to f multiplied by f multiplied by f n times. Okay, and we can write by this notation. This is very easy because any f from this set to f, we know that fi must be belong to f. Okay, so that, and we have f1, f2, fn. This is the image of this f. So we can write this by this n tube, so that we have Rn or Cn. This is a special case of previous. Example. And also if we consider z plus instead of x, we have the vector space of all sequence, because we know that any fn equal to the set of all f from n to x, and these are sequence. Okay, the set of all sequence fn, for example, fn belong to f. Okay, the set of all sequence in f. This f is R or C, and we have the definition of subspace. Okay, let me continue in the next session the definition of subspace and other definitions. Dear students, do you have any questions? Do you have any questions? In the next session, okay? We will continue in the next session, inshallah. Thank you very much. Thank you for your attention and goodbye for now.